Okay, let's begin. So I don't know how much of a recap to give. I don't want to spend too much time at the beginning of each lecture repeating material from previous lectures, but it is always a bit helpful. So the context here is, what we're discussing is computing, so designing logic circuits that operate on random bit streams. Given, let's say, inputs x1, x2, and x3, we're going to design a circuit that consists of just familiar ordinary logic gates that operates on these bit streams. It does so in a very ordinary sense. So the technology is not magic. A gate behaves like a gate. So if an AND gate receives two ones, it produces a 1, etc. And then we're going to look at the output, which is going to be some bit stream. Now, when I say a random bit stream, I guess that can lead to confusion because implicitly when I say random, people might think that I'm assuming that it's perfectly random, or stated differently, that the probability of a 0 versus a 1 are equal. So it won't necessarily be perfectly random. It won't be like an unbiased coin, to use the jargon of statisticians. It can be random, but it can be a weighted random bit stream where the probability of a 1 might be greater or less than the probability of a 0. But it's still random in the sense that we can't fix for each bit that we see or we receive, whether it's 0 or 1. We could just describe that as a probability. So given inputs, let's say x1, x2, and x3, what comes out here is going to be some function of x1, x2, and x3. It's obvious that the bit that comes out is a function of the bits that goes in. And I think it's perfectly intuitive that the probability of what comes out will be a function of the probabilities that go in. That's not quite so obvious. Can anyone comment on that? So, Akash, right? Yeah. So why is the probability of what comes out a function of the probabilities of what goes in?
If you're acting upon what goes in.
Yeah, I know. So stated this differently, it seems utterly obvious, but there can be, well, so this is not an interesting observation, but suppose that I didn't connect any of these wires inside. Then what just came out would be, let's say, all zeros. So then it wouldn't be a function. So how would you go about just making a proper argument that what comes out is a function of what goes in the sense that the probability of what comes out is a function of the probability of what goes in? How would you go about proving that, maybe for a specific circuit? I know. It's especially frustrating. I ask questions constantly. Especially frustrating when I ask one that either seems so obvious that there's nothing to say or you don't even know what I'm asking. Is that anyone else?
Is it because you're considering an infinite set and it's totally random, so whatever is going is nothing but probabilities?
Right. That's good. But what I was going for more was the fact that I haven't drawn the contents of this box, but let's say I do draw the contents of this box. Say these two go into an AND gate. This one goes into an OR gate. Then you can look at each component. And for each component, you can make the observation that for an AND gate, as we discussed last time, the probability of getting a 1 at the output is going to be equal to the product of the probabilities of getting 1s on the inputs. So for each AND gate, it has the feature that the output is a function of the input, in the sense that the output probability is a function of the input probabilities. And then if everything is connected, so if I have the wire at the output being connected to the inputs, it's then an inductive argument, to use the mathematical jargon. You can argue that if it's true for each gate, and then it's true for the next gate that you add, the next gate, the next gate, then it's true as a whole. Okay. But there's actually something interesting to be said about the function that is produced here, the type of function as a function of the input. So I'll be talking about that today to some extent. But I want to keep this interesting, and perhaps that's not so interesting. So last time at the very end of class, I showed this construct, and I didn't have time to explain it properly. It's unfortunate that I'm beginning the class with essentially what is perhaps an intimidating construct, an intimidating concept. So I want to take the time to really explain this properly. Don't feel that this is going to be representative of the class where I'm going to be showing you relatively complicated circuits with math. It really won't be representative of the course. We'll be focusing more on interesting concepts and puzzles throughout. But since I chose to begin with this, let me explain this properly. And to do that, let's have a little warm-up exercise, which I think most of you will have seen, but perhaps like many of us, it's forgotten in the mists of time. And you guys are young, so the mists of time are just a little shallow fog. But, and I know that, so North Americans were taught to use the notation N choose K. So this is read as N choose K. I think Asian students are taught the notation, there's different variations of it, but with a capital C and a K. Can someone help me? So this is how you learned it, right? But there's also an alternate notation. I don't know if it matters, but I think the N is put here. You're nodding your head. So is this how you're familiar with it? Yeah. It's perhaps a better notation than this one, because this one, these are parentheses, not square brackets. But still, in a paper, sometimes people assume that it's a vector with 2 entries. And it can throw people. So maybe this is the better notation. But this is the more common notation in North America. So it's read as N choose K, where N is an integer and K is an integer less than or equal to N. So let's just spend a little bit of time reminding ourselves what is the formula for computing it. And if you guys can humor me, let's remind ourselves why. Yes, in the back. Do you have a question or comment?
Want me to give you the formula?
Yes. Yes. What's your name first? Alex. Okay.
Isn't it n factorial divided by n minus k factorial?
So n factorial over k factorial, n minus k factorial. Okay. All right. So first, let's remind ourselves what the exclamation sign is. I'm not going to make the joke that every high school teacher makes. I just won't make it. You guys all know it. I'm not going to make it. All right. So what is n factorial, Alex?
N factorial is n times n minus 1 times
Perfect.
n minus 2, all the way down until it's just multiplied by 1.
Perfect. Okay. So knowing the definition of factorial, help us. This isn't a proof, and mathematicians are, I guess, would be uncomfortable with an emphasis on understanding anything that you write down this way, but it's helpful to understand things. So Alex, can you remind us what does n choose k mean? And why does this formula compute it?
This formula, this is a combination, if I remember right.
Uh-huh.
Or is it a permutation? It's a certain number of unique sets you can create.
Perfect.
Where you have
That's
n
good.
total choices,
Good.
and you must choose k of those choices.
Perfect. Very nicely said. I think you got that correct in every sense. So we have n objects. So let's say we go for 5 objects where these are our 5 objects. So these are our 5 objects, and the goal is to choose 3 out of the 5 objects. And what this formula tells us is the number of ways of choosing, so this would be 5, choose 3. It would be a number of ways of choosing 3 out of 5 objects from this set. Okay, so you gave a good definition of it, but why the formula? Does anyone remember? What's your name?
Jacob.
Coffee and what does it say on your t-shirt? Okay, that's not going to help me remember Jacob. Okay.
So you start off with arranging everything in a line.
Perfect.
And then the number of ways you can arrange them in a line is n factorial.
Okay. So let's not spend too much time on that, but that's really the crucial observation. The factorial is the number of ways that you can line things up in order. Does that make sense? Because initially you've got n objects. If I'm going to line them up in order, who's going to be at the front of the line? Well, I've got 5 choices. After that guy's in the front of the line, then I have 4 choices for the next, 3 choices for the next, and so forth. So n factorial is the number of ways of lining up things in a line, in order. Okay, go on, Jacob.
And then there's going to be some division between the things that you're including and the things that you're not including.
Perfect. And that division is really at the heart of what we're doing. So in choosing k out of n objects, we're discussing the number of ways that we can partition n objects into k objects that we choose, n minus k that we don't. So k happy children and n minus k unhappy children. So all of you American students, you've all been subjected to the humiliation of forming a sports team when 2 captains are selected and the captains get to choose their, and you know, like I mean, as popularity contests go, you're sitting there and you're hoping that you'll be chosen early on. You won't be the last kid left there standing that neither team wants. Okay, so the k is the team that we're choosing. The n minus k are the kids who aren't chosen for the team. So the process here is to divide it into 2 sets, so the k and the not k, so the n minus k. So again, why the formula on top is the number of ways of lining up all the kids in order, and then discuss so that's the numerator, the denominator.
Yeah, so there's going to be the line that divides the ones that we're choosing from the ones we're not choosing. But the thing is, on either side of that line, you can rearrange them without changing the actual choice. So we're counting by the number of rearrangements there are.
Right, perfect. So the reason why we divide is that we're interested in partitioning the 2 sets. But in the numerator, we've computed the number of ways of lining up all the students. So given any partition, the order of the students in the partition doesn't matter. So we divide it by the number of ways of ordering the chosen children, and we also divide it by the number of ways of ordering the unchosen children. Okay, let's not spend more time on that. But n choose k is something that we're going to use to explain how this particular construct works. To do that, let's have a little bit more fun. So Jacob, can you help us a little bit with Pascal's triangle? And what is the relationship between Pascal's triangle and n choose k?
Let's
So-
see, the n choose k is the nth entry of the, or kth entry of the nth row or something?
Right. So as we step down, so first someone help me. I always mess this up slightly. Someone help me write out Pascal's triangle. So 1, then what comes next? 1, 2, 1.
All right, 1, 1.
That's what I always mess up. 1, 1, and then 1. Okay, next.
No, it should be 1, 2.
It's only 1, 2.
You add 1 every row. You add 1 digit every row.
Add 1 digit every row. Okay.
1, 3, 3, 1, 1, 4, 6, 4, 1. Follow the addition.
You do it for me.
5,
5, 10,
5, 10.
10, 5, 1, 1.
Okay, all right, let's stop there. All right, so Jacob, what is the interpretation of Pascal's triangle in terms of n choose k? I think you had it a second ago.
Yeah, the k is which number you're choosing, and n is the row. That
Right, so this is n equals 1, this is n equals 2, n equals 3, n equals 4, 5, 6. You'll notice that, so we were right here, and this is 1, 2, 3, 4, 5, 6. So the number of entries in each row is what we've chosen for n. And as we step along, the entry that we're at is the k in the n choose k. So this is the number of ways of choosing 1 out of 6 objects, 2 out of 6 objects, 3 out of 6 objects, 4 out of 6 objects, 5 out of 6 objects, and 6 out of 6 objects. So it starts at 0, yeah. No? I think this is right. So, yeah. Why 0?
Let's see. Like ways of choosing 0 things out of a set is 1, and then ways of choosing like 6 things out of a set is
Oh.
also 1.
Yeah, are you right? Yeah. Okay, thanks, Jacob. That makes sense to me. Okay. All right. So this is the interpretation of n choose k. Now, just another quick digression. Can anyone help us remember what is the relationship between n choose k and counting in binary? Or, stated differently, what can you say about powers of 2 and the sums of these rows? Can anyone quickly in their head sum up? Let's take just the total sum of the number of integers in each row. So this is going to be 0. This is going to be 2. What's this going to be? 4. And this is going to be 8. And this is going to be 16. And this is going to be 32. So you notice that these are powers of 2. That's not a coincidence. And by the way, you could spend an entire lecture looking at the symmetries and interesting properties of Pascal's triangle. Has anybody ever heard of the powers of 11 argument on this? So as you go down, you have to fudge things a little bit. But the fudging is simply you have to start sliding together some of the columns. But Pascal's triangle gives you powers of 11 as you go down. So that's really fascinating. And then all kinds of other symmetries. So you can get the square of a number by looking at the adjacent and the lower value, and so on and so forth. But anyways, let's focus on powers of 2, because this is actually the explanation that we'll need here. So I'm going somewhere with this. So Jacob, what is the relationship between the fact that the numbers sum up to a power of 2 and the entries in that row?
Because there's probably some relationship with the row and the row above it, that since they're sums of the previous row.
But let's focus on counting in binary, because this is, so I'm going somewhere with all of this. If we count in binary, so let's count in binary up to 16. That'll take us a little while. Okay, so this, for the non-computer engineers in the audience, was counting in binary, simply listing all binary numbers from in decimal 0 to 15 down here. Now, so let's erase this row, because we'll focus on the 16 row. So, Jacob, can you see now why the sum of this particular row is going to be 16?
Since every number is the sum of the two numbers above it, that means that every number gets added twice to the row below it. So it moves every time.
That's good. But because this is finally what we're going to need in the construct. If we look at the numbers in binary from 0 to 15, let's focus on the number of 1s in the binary digit. So up here, there are 0 ones in the binary digit, the binary number. 0 ones in this binary number. Here, there are 4 ones in the binary number. And so here, there are 0 to 1. This is the number of ways of choosing 0, 1, 2, 3, 4. So there's one way of choosing a number that has 0 ones. There's one way of choosing a number that has 4 ones. And in between, what do we have? So how many ways are there of choosing a number that has a single one? Jacob, 4. Why? Well, we can have this guy. We can have this guy. We can have, in between, there's this guy and there's this guy. 4 ways of choosing a binary number that has a single one. How many ways of choosing a binary number that has 3 ones? Well, we're going to have this guy, and this guy, 4. How many ways of choosing a binary number that has 2 ones? Well, we're going to have 6 of those, which is going to be the remainder. So n choose k, I think quite intuitively, tells us the number of ways that we can write down in binary a number that has k out of the n digits being 1. Does that make sense? And so we have all the numbers in binary, and all the numbers in binary has to include all the choices of 0, 1, 2, 3, or 4 ones. And so the total number of entries that we have here has to sum up to the total number of entries we have here, which means that this row of Pascal's triangle has to sum up to 2 to the power n, because we have 2 to the n rows. OK. Maybe you guys are not so excited by discrete math here. But this is the property that we're going to use in the construct up here. OK, while I catch my breath, because I really didn't explain this properly, does someone want to take a crack at explaining it before I explain it, based upon what I said last time? So Akash, do you want to take a crack at it? Nope. Fair enough. Jacob? Let's remind ourselves what's going on here. For better or for worse, I'm showing you the construct after I explain to you any of the math that we're going to use. But to remind ourselves, this is going to be a circuit that, given input bit streams x1 through xn, which are all bit streams that have probability t. So we're going to have multiple bit streams, each of which has the same probability of a 1 as a 0. We're going to compute as a function of t the output y. That function of t that we compute is going to be a polynomial. And I'm going to argue that we can implement any polynomial this way. So it's a design problem, which means you give me a polynomial. Remember the example from last time? Something like 0.8 t squared minus 0.7 t plus 0.3. So you give me any polynomial. This is going to be a way to implement it. So normally I would show you how we massage the polynomial. But instead, I want to explain to you the circuit. And then after showing the circuit, you can just look at the math. All right. But as I've been babbling, anything, Jacob? OK. It's going to be hard. I mean, it's going to be hard for you to make that leap without me explaining it. All right. Up here in the top right corner, we're going to have just top left corner, sorry. We're going to have an adder. The adder, what it's going to do is given n copies of the input. And to keep this simple, I'll just annotate this as t, t, t. So these are going to be input bit streams that are all random, but each has probability t. There's going to be n of them. What will come out of this adder will be simply a count in binary of the number of ones that we see among these t inputs. My lowercase t's look ugly. I don't know how to write things in lowercase. I really don't. So you guys have heard my little... So I learned to write in Europe in the first grade cursively. And then I know how to write in capital letters. But all Americans, they learn how to write in both upper and lowercase. letters in block characters, not in cursive, and I just don't know how to do that. Okay. All right, so outcomes here, and let's make this concrete. Let's go for 8 instead of n, because 8 is easier than n. So each of these has probability t. So out comes 3 output lines. Well, in fact, yeah, this is what I got tripped up before. We'll actually need, I guess, 4 output lines, because we have to represent a number that can range from 0 to 8 inclusive. So we'll actually need 9. Well, the range of numbers that we have to represent is 9. All right. So the number that comes out here will simply be a sum of the number of ones that we see on the input. So it's not the adder that you might expect from digital design, where we add 2 numbers and get the sum. This is going to be more like an accumulator. Well, let's just call it an adder. So this is a circuit that produces here, in binary, a count of the number of ones that we see here. So this is a set of outputs that can range from 0, if we see all zeros here, or it can range up to 1, 0, 0, which is going to be the decimal 8 that we see here. So we can have either all zeros or all ones or anything in between. That's the number that we can get here. Now so that's the block that I have at the top right. That block is going to go into this block. So Jacob, remind us, what is this block?
It chooses which input to send to the output.
Yeah. So it's just a chooser. So let me draw a big chooser here. So these guys, I'll just collapse them all into a single line, feed it in here. So these 4 lines go in here, and now these 4 lines can select between 0 and 8, from 0 to 8 inclusive possibilities. So we can select this line, the 0 line, the 1 line, the 2 line, 3 line, the 4 line, the 5 line, 6 line, the 7 line, or the 8 line. So these are lines that I've numbered according to the number of ones that we see on the input, which translates to a sum of those, and that sum then selects the appropriate line. But that's all I've done here. So it's really not that complicated, I hope. So are the non-computer engineers okay with this? Just give me feedback, honestly, because this is a pure circuit construct. It was though, for any of us, sitting in on a chemical engineering lecture, I could only imagine how lost we would be. We'd understand nothing. Okay, all right. So here, we're going to have random bit streams coming in. These random bit streams are going to be random, but they're going to be constant. So what do I mean by that, Jacob? So what I mean is, we're going to assign a coefficient to them. But that coefficient is not going to be a variable. It's going to be a coefficient that we choose ahead of time at design time and then remains fixed. And these are going to be the coefficients in our polynomial. So everybody's okay with the concept of a polynomial. A polynomial is something like 8x cubed plus 7x squared plus 3x plus 1. So these are coefficients. The coefficients that we'll have, well, first of all, they have to be between 0 and 1, and there's going to be massaging. But what I mean here is, in a polynomial, you have coefficients. Those coefficients are numbers. They're constant, in the sense that you decide upon the coefficients, and then you're given the polynomial. So that's what these will be, these inputs to the chooser, to the mux. Those inputs will be constant in the sense that you'll have bit streams, which will be random bit streams. You'll have a bit stream that consists of zeros and ones flowing in. But the probability of a 1 versus a 0 will be fixed, and it'll be fixed to a particular coefficient. and you can have different coefficients. So, and those coefficients, let's just call them, I'll use uppercase, that might confuse you guys, lowercase b0, all lowercase b1, all the way up to b8. So these coefficients are what we get to choose at design time, and these coefficients determine the polynomial that this circuit implements. Okay. But what polynomial does it implement? So step in, Jacob. What is going on here? And that formula at the top, if you guys can read it. Yeah, go ahead.
So the adder is going to add up a bunch of independent ones or zeros, which gives the binomial distribution. So that means that, and since the count that it gets is choosing which B that it outputs, or
Yeah.
It's choosing one of those with the probability distribution based on that.
Perfect. Very good. So here, if we ask ourselves, here we're going to have 8 independent copies that have probability t. If we pick one of those, if we pick a count of one of those, so let's say we pick a count, well, actually, we should go for 8. So let's say we pick 0, 0, 1, 1, 1, 0, 0, 0. Okay, so here, suppose that this, let's turn our heads sideways here. So these are the 8 bits that we received here. What is the probability of getting this particular bit stream? Can anyone say? Pardon me?
Or that particular.
Yeah.
2 minus 8.
2, go ahead. The probability of getting a 1 for each bit is going to be t. So what's it going to be here? It's going to be 1 minus t times 1 minus t times t times t times t times 1 minus t times 1 minus t times 1 minus t. That's the probability of getting this. They're independents. We can just multiply them. I told you in advance that the probability of getting a 0 versus a 1 on each line is going to be t, so that the one entry, these entries are just t's. The 0 entries are 1 minus t's. So the probability of getting this particular entry, if I collect these out, is going to be 1 minus t to the power 1, 2, 3, 4, 5 to the power 5 times t to the power 3. We all agreed upon that? So you can see this part of it, where that's going into that formula up there. So we have the t to the I, that's choosing, I'm mixing my k's and my i's, which is very bad here. So n choose I is going to be the number of ways of choosing I out of n. So I here is going to be the number of entries that are 1. The probability of getting an individual, a specific bit stream, is going to be 1 minus t for the zeros, raised to the power of the number of zeros, times t raised to the power of the number of 1s. That's for this particular entry. But this particular entry, since we don't really care where the number of 1s are, is just going to be an entry that has 3 out of 8 entries being 1. How many ways are there of getting 3 out of 8, Jacob? 8 choose 3. And so the number of this is going to be the 3 entry here. So this will choose this particular bit stream. The number of ways that I can get 3 out of 8 will be 8 choose 3, what we went through. That's the number of ways that we can get 3 out of 8 bits being 1. And what is the probability of each one of those bit sequences happening? Well, it's going to be t to the 3 times 1 minus t to the 5 here. So this is going to be the number of ways that we can get 3 out of 8 bits times the probability of each of those happening. That's this case. This case is going to be any one of those bit sequences that give us 3 out of 5 is going to sum to 3 out of 5. And we're going to select the 3 entries. So we're going to select this particular bit stream. And so now what is the probability of getting a 1 versus a 0 in this bit stream? Well, it's just going to be b to the 3. So this particular entry, and it's going to be a summation. There's a summation sign down here. The summation sign is going to sum this particular entry in the summation sign is going to be b to the 3, which is the probability of the bit stream that I feed into here, times the number of ways of getting 3 out of 8 bits being true, times the probability of that outcome happening. So it's the probability of selecting a line, which is this, times the probability of a 1 versus a 0 on that bit stream. This is one entry. And then to get the full formula, what I'm going to do is to sum over all n cases. People following that? All right. So I could state that again. I get that this is kind of, in retrospect, I regret taking this concept and throwing at you right at the beginning of the course, because I really won't be doing that much of this. But any questions? So Akash, any part of this didn't make sense? OK. Now, this, once we write this out, this is going to be an expression. But it doesn't really look like a polynomial, right? The polynomial, this looks like a polynomial. That doesn't look like a polynomial. So any thoughts on that? What's your name in the front row?
Alex.
There was another Alex. Where was the other Alex?
Back here.
Thanks, Alex and Alex. So what kind of polynomial will this be? Or what is the relationship between this and a regular polynomial?
It's only just how we're going to powers.
Yeah, exactly. Let me pull up the slide. OK. So the full explanation is that this is going to be a polynomial that we've just packaged differently. And what I'll step through without really emphasizing any of the details is that we can take any polynomial of a given form like this and repackage it in the form that we need like this. So let me begin with an example. So suppose that this is your polynomial. And this is a polynomial that we recognize, a 3 minus 8, a plus 6. We're all good with that, I think. But I'm saying we can convert any polynomial. That's not true. There has to be very specific restrictions on the polynomial. So Jack, what are the restrictions on the polynomial? So if, like for instance, if I said, give me 3t plus 8t squared plus 6t cubed, you could say can't be done. Why?
I'm not sure.
Anyone else? Imaginary, Scott. Yeah, why? It's a probability. So whatever falls out of our circuit is going to be a bit stream. And whatever falls out of the circuit, if it's a probability, it has to be a number between 0 and 1. So it's not so much that the polynomial always has to evaluate to 0 and 1, but to the interval 0 to 1. But it better evaluate to the interval 0 to 1 if the inputs evaluate to 0 and 1, because the inputs are probabilities. So the requirement is if the input is t along the x-axis, I've committed a cardinal sin here, which is not to label my axes. If the input is t along the x-axis and the function g of t is along the y-axis, we better confirm that if t is between 0 and 1, then g of t is between 0 and 1. But as it turns out, that's the only restriction. The method that I'm taking so much trouble to explain to you is a method that works in the sense that if you give me any polynomial, you can just sit down and plot it, see that it's between 0 and 1 for 0 and 1, then we can implement it this way. So how do we implement it this way? Well, I'll show you the steps and then skip over the math. The steps are that we're going to, first of all, repackage the polynomial. We're going to repackage it in the sense that we're going to re-express it instead of powers of t, we're going to express it as powers of t times powers of 1 minus t. So we're just going to repackage it as t times 1 minus t. The way to do that, I'll show you. It's a formula to do it. So here, the B13, B23, B33 are each going to be t times 1 minus t, powers of t and 1 minus t. So that's what it is. I'll show you that in the next screen. Once we do that, then we sometimes have to massage it a little bit further. We have to massage it a little bit further in the sense that just expressing it, repackaging it as powers of t and 1 minus t, sometimes gives us an expression that has numbers that are greater than 1 or less than 0. And recall that each of our coefficients here, being a probability value, has to be a value between 0 and 1. So we'll massage it further. So in the next step, I've massaged it further. And then here, massaging it further, it got us a bit closer to our goal, but there's still the minus 1/4. But as it turns out, if we massage it just a little bit further, we get coefficients that now are values between 0 and 1. And we can take those coefficients in this form and now directly implement it as a circuit. So these are now all coefficients that are in the unit interval, 0 and 1. So we can implement it. OK, so I think I'm stepping through the same example, but here with powers of t. So just take it on faith for a minute, because in fact it's just a formula. But given any polynomial up there, we can plug it into a formula and get the polynomial here, which is coefficients times powers of t. It's going to be t to the 0 times 1 minus t to the 2, t to the 1 times 1 minus t, and t squared times 1 minus t to the 0. We can take that, and we can observe that these are the Bernstein basis polynomials. So this is simply n choose I, where it's going to be 0, 1, and 2, times t to the I times 1 minus t to the n minus I. And then call those b's, Bernstein polynomial. But here the coefficients are not in the unit interval. So in this case, we can massage it. And after massaging it, we now have coefficients that are all in the unit interval. Okay. The massaging of the polynomial, just bear with me for a moment. But is it clear to everybody that once we have it in this form, we can implement it with this circuit? Because that's actually the interesting part of it. Meaning that once we've taken our polynomial and converted it into a form with the t and the 1 minus t powers, with an n choose I in front, and with these coefficients all being in the unit interval, then we just plug it in. So what do we do to implement our circuit? Well, the whole point here was to figure out what these coefficients are: 5/8, 0, 1/8, and 1. Once we have those here, then we just plug those into our circuit, and our circuit implements the polynomial. Okay. So let me go backwards and just show you guys the math of it. So the math of it. This is called, as you've seen me flash the name, a Bernstein polynomial. This is, in a sense, it's not elementary math. It's certainly not. But Bernstein polynomials, this is a topic that would be taught. It's mostly of interest to people who do graphics processing. So people who do, in these days, graphics processing are used for computer games and so forth. They use this type of packaging a lot. So when I Googled Bernstein polynomial, that's where it's taught. But there's nothing especially magical about it. So it's simply an alternate way to express a polynomial, where instead of just writing down a power of x, let's say, your basis term, so the term that you use in your sum, is always going to be an n choose I, t to the I, 1 minus t to the n minus I. And then you're going to express that as a sum of those with the b coefficients in front. OK. Now, so this slide actually gives you the formula on how to convert. I won't attempt to explain it to you because it's not interesting. But given an ordinary power form polynomial, such as this one, so here If we take this ordinary polynomial expressed as powers of x, there I've got it as powers of t. So it's just a sum of the ai's times powers of t. We can obtain the Bernstein polynomial, which is going to be a sum of the coefficients, the bi's, times this packaging of t times 1 minus t in front. We can obtain it just by computing each bi, which is what we want, from each of the ai's, which is given here. And this formula is just a formula that gives you how to compute the bi. So for the bi, we're going to have to sum it over all of the a coefficients, and then we've got an I choose j and n choose j at the bottom. And the derivation of this would be for a different course. But all this to say that obtaining the Bernstein polynomial is not difficult. You just plug it into this formula. And this is exactly what you'll be asked to do. You'll be asked to essentially go through the formula here to obtain the Bernstein form and then draw the circuit. You'll be asked to do that on the first homework. OK. All the slides will be up, so don't be afraid of computing any of this. OK. But what was the other step, if anyone is following? So, Tora, what was the other step that we had to do?
So where are we at in the computation?
Good question. So where we're at is here's where we're at. We're given, this was our polynomial, regular power form polynomial with powers of t. We plugged the coefficients, the ai's, which are 5/8, 15 over 8, 9 over 4. We plugged those into the formula that I just showed you. And we got this, which is an expression in terms of the b's and the packaging. But what do we have to do next? I just called it massaging. Yes, yeah? There's a negative coefficient. So we have to massage this expression to get rid of the negative coefficients. So as it turns out, to do that, all you have to do is to bump up the degree. So here this was degree 2. If you bump it up to degree 3, degree 4, degree 5, as it turns out, you always get an expression with the coefficients in the unit interval. And the bumping up is exactly what we're doing here. So this is the bumping up. You guys can't see that. It's very annoying. So the Mac does this mirroring of displays, but I wonder how I found it. So this is the bumping up, which means given the Bernstein polynomial with an expression in terms of the b's, if we bump up the degree, so we go from degree 2 to degree 3, here's the formula for doing that. It's for obtaining degree 3 in terms of degree 2, or for degree 4 in terms of degree 3. Again, the math is not interesting. It's just, you can do this with power form polynomials too. You can bump up the degree of the polynomial by computing an absolutely equivalent polynomial, but of a higher degree. If we keep doing that, then, as it turns out, it's a big mathematical proof, we always get coefficients in the unit interval. We can always implement the polynomial. Okay. All right. Let me, unless there are questions on this, let me skip forward to some applications, some more interesting stuff. But any questions on this? Scott? So this was early on in the research that I did with my students on this topic. Our question was, if we decide to implement circuits with computation over bit streams, well, how do we implement anything? And the fact is that working with random bit streams and probabilities is completely different. So you can't just take a standard design for a circuit that computes something and immediately come up with a circuit that operates on probabilities. Because in the standard design, as I started off by saying, you encode numbers in binary, and here you've got probabilities. And the function that you need will be a very different function if you've expressed it in binary versus probabilities. So anyways, this is what we came up with, this entire scheme with the Bernstein polynomials. But here's the example. So suppose that we wanted to implement t to the power 045. I'm not showing you the steps, but the first step that we would do would be to convert this into a power form polynomial, an ordinary polynomial. After doing that, we would go through the exercise that I came up with, but as it turns out, here are the coefficients that we need. So B0 through B6, we would need 7 coefficients. These are the values. We plug those into these inputs and feed in multiple independent bit streams, and we get this function, which is the gamma correction function that I talked about. It's a function that takes a value and raises it to a power. And this is an incredibly inexpensive implementation of this particular construct. Inexpensive in the sense that this circuitry, it seems complicated here, but imagine the circuitry that would compute a Taylor series expansion of this function and all of that. This is much less expensive circuitry. But there's another benefit. So can anyone talk to us about fault tolerance? Does anyone have this particular expertise? So Alex in the back. What is fault tolerance, and why would you want a digital circuit that tolerates faults?
So not every little bit that goes into or out of your system is going to be what you want it to be. There are going to be some that are zeros. There are going to be some zeros that are ones and some ones that are zeros. And fault tolerance is how many incorrect bits can you get before you experience a system failure.
Perfect. Oh, very nicely put. I was just told before this lecture the Unite students won't hear the student responses. So especially bad when I say perfect. You said this as well as I could, and I'm not going to repeat it. But that's what I'm going to do here. So that said, the more interesting question, Alex. So in terms of the stochastic bit stream representation, random bit stream, versus a binary representation, a positional representation, what would you expect will be the performance with respect to errors? And to repeat for the Unite students, here are fault tolerances. Suppose that we're running a computer system, and some little genie or devil comes and randomly flips a bit from 1 to 0. This is a big area of research because something that computer engineers aren't advertising to the general population. Computers that contain our billions of transistors these days are failing. They're failing in many ways. They're failing sometimes due to age. So Apple wants you to replace your iPhone, I think, every 18 months. Spend $600 every 18 months. But in general, computer systems that are being built these days, unlike the computer systems from 30 years ago, the actual silicon is aging. And it's aging because it's down to a few nanometers in thickness for the different layers. And there are layers like the metal oxide layer. And that layer, simply, if you continue to use the circuit, it gets hot, is degrading. And so chips that are coming out these days really have a finite lifetime. You can measure it in terms of how long they'll be used. One way in which they start to fail is they don't just fail catastrophically. They don't burn or melt. But individual transistors don't switch when they're supposed to, or sometimes switch when they're not supposed to. So you run your circuit, and it's hard exactly often to pinpoint where the error has occurred. But a 0 to a 1 mysteriously gets flipped. And you run it again, and it's all fine. You run it again, it's all fine. And then the 10th time you run it, a 0 gets flipped to a 1. It's a real problem that the industry is facing, and one that they're not advertising. I'm sure that the people who make the control circuitry for launching nuclear weapons, they're really interested in this. Because there's some applications where we really rely upon electronics for our lives and our safety. And they're failing. So a lot of researchers, including myself, are looking at ways of implementing fault tolerance. And that was the original motivation for getting into these randomized bit streams. But why? So why could a randomized bit stream be really good when it comes to tolerating faults? Yes, your name is? Brian or Ryan? Ryan. And when I taught the class last semester, so where's the Ryan? I had like 15 Brians and Ryans in the class, and I just couldn't get it right. So it's Brian or Ryan?
Ryan. No.
Ryan, okay.
Well, you've got these giant random bit strings, so any small differences, you probably have quite a few, and it wouldn't really change the probability.
Yeah, so can you say more about that? How will a random bit flip in a bit stream, how will it affect the value that you're computing on with the randomized bit stream compared to a binary string? So with a binary, so if you represent a number in binary and you flip a bit, what can happen?
Oh, change the number.
By how much?
Depends which bit.
Very good. So suppose that you flip the rightmost bit.
Very small.
It'll change it by 1.
Yeah.
What if you change the leftmost bit?
Negative 2 times.
It can be positive or negative. But it'll change it by half the amount in the range that you're representing. So let's say you're representing numbers between 0 and 1024. If you flip that last bit, you will change it by 500. So, and that's an inherent weakness of the positional system. If you have a positional number system, recall last time I had the human versus the caveman, the positional number system is one in which it's very compact, so we can represent large numbers with just a few digits. But it makes, especially the high-order digits, extremely vulnerable. If you mess with those high-order digits, you've changed the number completely. And in computer systems, this could be a real problem. You know, if you're experiencing, over the lifetime of a circuit, random bit flips that are almost impossible to predict when they'll start occurring, to what degree they'll start occurring, or where they're going to hit you, and you choose to represent your numbers in binary, well, that's the bottom example here. So the bottom example, in this case, you could take a real hit if you flip the leftmost bit. And I think it's perfectly intuitive that in the random bit stream case, you take much less of a hit. And so let me play devil's advocate here. The bit stream is random to begin with. And so a bit flip shouldn't hurt you at all. Can anyone disagree with that? So Tor, why would you disagree with that statement?
You're still representing a number, so it's not indicative of.
But you
Trying to represent.
play devil's advocate, right? I know the answer I'm going for, but I'm trying to say the opposite. So it's random. You want it to be random. The more random, the better, right? So you flip a bit, and where you flip it as random, this should just not change the value at all or even help you.
Well, that kind of only applies for values close to 0.5.
Perfect. And so it does only apply to values at exactly 0.5. Wrong class? Sorry.
Yeah, wrong group.
Wrong.
Sorry about that.
No problem. So if you have a bit stream that has exactly probability 1/2, so I don't know if this was exactly 1/2, but I tried to make it so that we will have roughly the same number of ones as zeros. It doesn't mean you're always going to have a 1-0 alternation, but it means you have almost exactly the same number of ones and zeros. And then the bit flip, when it happens, it picks a random bit and it flips that bit. If the value you're choosing to represent is exactly 1/2, then nothing happens on average, probabilistically. So at 1/2, these circuits are perfectly immune to bit flips. But of course, that's just one case. And so Tor, what happens if you're trying to represent the value 0?
And you get a bit flipped to 1.
To 1.
So it's
And so when you're close to the extremes, when you're down at 0 or when you're close to 1, in these cases, a bit flip immediately hurts you. But it doesn't hurt you nearly as much as it does in the case of a positional system, because in this case, if you're trying to represent the value 0 and you've got a long stream of all zeros and you get a single 1, well, it nudges you a little bit away from 0. In fact, the amount of damage the bit flip does is exactly proportional to the length of the bit stream. So that can be justified mathematically, but in a sense, it's extremely intuitive, I think, that if we're using random bit streams, and this is partly owing to the fact that it's just a very long bit stream to represent a given number, but the bit streams are inherently very immune to bit flips, or at least the damage that a bit flip does is very small. And that's part of the huge penalty that we pay, because we need a very long bit stream to represent a number, but we get this fault tolerance. And so, as I said, this was the original motivation why we considered this whole topic for research. But a disclaimer here, I'll spend a little bit of time in this lecture talking to you about it, but this is the aspect that I'm least excited about for this topic. Just because after we got good at building circuits like this, as I said last time, we can build circuits that have a 100x reduction in terms of the number of gates. And that's really exciting, that we can do very complicated functions with very simple logic. I'll show you some examples. But first, let me step through, again, some boring slides on just fault tolerance. And for the non-computer engineers, I think what I'm showing you here are constructs that I've shown you. But don't worry about the specifics of the constructs. Or maybe we should, actually. So this will be a good quiz question for the first quiz, which is coming. We're going to do, by the way, the quizzes for the class. The decision was made. We're going to do them all online. So we won't take up class time, and they'll be on the Moodle site. You just get to go and take the quiz on the Moodle site. But all the same caveats apply. You can take it as many times as you want, and so forth. OK. But So ignoring the bit streams here. So Jack, so mathematically, could you tell us what function this computes? Or if I give you probabilities, could you tell us what this computes? And I guess it's messy here because I've shown you the bit streams, but you've got x1, x2, x3, and s.
You mean like, okay.
Oh, actually, I've got the formula up there. Yeah. Oh, shoot, OK. I didn't know I had it. So, but is it clear to everybody how you would compute the formula that the circuit computes? Sorry, that was redundant. So Jack, how would you do it?
Well, I mean, you kind of just demonstrated with the derivation from the other.
Yeah.
So
this isn't quite, like, I mean, it obviously has a similar structure, but not quite. So what you would do here is recall that an AND gate multiplies and a mux adds. So this is just constructing an operation that consists of multiplication and addition. So if you look at the top, it's going to be x1 times x2. That's going to be what the AND gate produces. And so it's going to be x1 and x2 times s, which is the one case for the select. Recall, should I write this down? OK, so multiplication for an AND gate, if we have A and B, this multiplies the two probabilities. This gives us A times B. If we have the multiplexer, and here we have X, Y, and S, this gives us S. This is the one case, 0 case. This gives us S times X plus 1 minus S times Y. So the formula that I have up there, all I've done is I substituted for the X case, I've substituted the AB, or I'm getting it all wrong here. Okay. X1, X2, X1 times X2. So I substituted for X, X1 times X2, and here I have an X3. And then the result is the formula up there. OK, so that's what this circuit computes as a function. And this is going to be a function that presumably we're interested in. And what I'm showing on this slide is I'm showing some bit streams that are flowing in. The bit streams, I've ascribed values to them, 4 8, 6 8, 7 8, 2 8. If you plug in those values into the formula, you should get 6 8. And then what I'm showing is the effect of a bit flip. So I'm showing the effect if we take one of those bits and we flip it. And you can see that the final result that we get is going to be 5 8 instead of 6 8 in this case. And this is not a contrived example. That's typical. That we're supposed to get 6 8, but because we flipped those bits here on the input, instead we get 5 8. Now, suppose that instead, and here is the circuit implemented in binary radix, where I've implemented the fractions. I'm writing the fractions in binary here. So here, 4 8, I'm written it this way. Now, for the non-computer engineers, you may not have seen fractions written in binary. But they can be written in the same way as integers. You just have a binary point and then a binary number. So here are the numbers represented in binary. And you can see that the numbers represented in binary are much more compact. But a single bit flip here on the x3 changes my value much more, from 6 8 down to 3 8. And that just makes intuitive sense. OK, for the fault tolerance. But let me show you some numbers on fault tolerance. OK, here is just, and this is obviously from a talk that was given at a conference where this work was presented, the full circuit that does gamma correction. We built the circuit in 2 ways. We first built the circuit the conventional way that you would build it, with adders and multipliers operating in binary as a positional system. Then we went and we built the circuit our way, which is with the Bernstein polynomials and all that mess operating on stochastic bit streams. And here are the two implementations. On the top is the conventional one. We call the deterministic one. And here we started to introduce errors. We started to introduce bit flips. We started to introduce bit flips at a rate of 1, 2, or 10%. So we're flipping 1% of the bits for this image, 2%, 10%. And as you can see, by the time we hit 10%, we're doing a lot of damage. And this makes sense. We're flipping bits. And as we flip the high-order bits, in a binary representation, we've destroyed the value. On the bottom, so typical for a conference presentation, top, bad, bottom, good. So in our case with the stochastic implementation, you can see that there's almost no visible effect. But there is a subtle visible effect. So can anyone see what is the subtle visible effect here? So Michelle, can you see any difference in the images?
Yeah, the last one looks gray.
Yeah. So why?
Because they're closer to the middle.
Closer to the middle. And that's exactly right. So I didn't explain it properly, but when we were talking about bit flips and how they affect values, at a value of 1/2, there's no effect. If you're over at 0 and a bit flip pushes you towards 1/2, if you're over at 1, then it pushes you down to 1/2. Bit flips push you towards the center. So here, there is an effect. The effect is that the bit flips have made our image grayer, which is the center part, made the blacks lighter and the whites blacker. But the argument is that there's still much less degradation. And as you might expect, the effect of the damage is very small in the sense that we never have an error of more than 25%, even if we go to very high error rates. It's just, stated differently, the amount of error that you get is never worse in a proportional sense than the error you introduce. And that was the effect we wanted to achieve here. OK. All right. Here's just a slide to boast in terms of what we've done. Ignore the top part. It's just the implementation. But here is a slide that shows the area. The area is the amount of area on a chip required to implement our functions. And here the between 2 and 3%. This is the amount of area that we require to implement these functions. And we presented this a while ago. This was really exciting, that we could implement a given circuit with an area of 4, this is a relative measure, compared to an area of 200, or 6 instead of 265, or 8 in terms of 331. So we can implement complex functions, and these were polynomial functions for image processing, with about 2% of the area, so tiny, tiny little circuits. And those circuits are very fault tolerant. So that's all great. But the downside is these circuits were slow, 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 slow. They're slow because you require very long bit streams to process it. So it's, in a sense, an extreme trade-off. All right, as usual, I'm running out of time. But I want to conclude with something fun and interesting. It's not this. This slide is just the good and the bad. So the circuit area is small, the error tolerance is good, the delay is long. So it's just a comparison of the two. But here's the research topic that I'd like to explore, and I'll try to bring as much as I can into the homework. In a sense, this is a radical trade-off that we've done. So we've gone from binary radix, which is very compact as a representation, and has the feature that we can build very efficient circuits in terms of the speed, because it's such a short representation. We've gone to what is, it can be called a unary encoding. It's caveman encoding. We encode the number by just the fraction of ones versus zeros, which is an extremely inefficient encoding. But in between, there are probably many types of encoding that we could explore. And the strategy is going to be to see if we can come up with encodings that are more efficient than the caveman representation, but perhaps less efficient than binary radix, but still allow us the property of computing, in a sense, almost magically. And the magical aspect of the computation is that we can do a complicated operation like multiplication or any other complex function, as I tried to explain at the outset, without decoding the value. In essence, the value that enters the circuit and we're operating on, we're essentially operating on it already in decoded form. We just already have the weight or the number of ones versus zeros. So that's what I'd like to explore. Okay. I was going to begin talking about sequential constructs here. But instead, let me ask you guys this, because I want opinions on this. So has anyone taken a computer architecture class here? So Alex, what is pipelining?
It's where you split up the instruction into smaller bits so you can do different steps of the instruction at one time.
So for the non-computer engineers, modern processors, they use a concept called pipelining, which I think is very intuitive to explain. It's simply that since you want your computer to run as fast as possible, you want it to run at a blazing speed, the concept of taking an instruction, which is what the computer does, it takes an instruction and it executes it, that concept is too lengthy of a concept, meaning to just have the computer take your instruction and then operate it and produce the result. Your computer runs too slowly for what you want. So instead, what you're going to do is you're going to have your computer take the instruction, begin processing it, and this is like a pipe, and then you'll begin processing the next instruction before the first one is completed. You'll just start the next instruction running through. Of course, there's much more to it than that. But that's the concept of pipelining. So can anyone suggest, with stochastic bit streams, streams of ones and zeros, what might you do in terms of pipelining? So Jack, any ideas?
I don't know. I'm thinking there must be some kind of analogy to having like multiple cores on a CPU.
Yeah.
Like to make this kind of encoding a lot faster.
Yeah.
But I don't know exactly.
So the idea that I'm pursuing now is the following idea. So imagine you've got the bit stream coming in. And think of it like a hose. So you've got, so this is your input coming in. So imagine it's like a sputter gun. It's just spitting out all sorts of different metaphors. But a sputter gun is a good one. So it just spits out ones and zeros. And the value that you assign, let's say it's a half for the current value. But then, as a result of the computation, perhaps there'll be feedback in terms of what you not want the next value to be. The next value might be a quarter. So what you could do, and this is the stupid way of doing it, you could say, well, let's choose a window size where we'll encode the value being a half. And then when we're done with that window, for the next window that slides in, we'll put in ones and zeros at a rate of a quarter. But instead, suppose that you just turn the dial on your sputter gun. So your sputter gun is spitting out ones and zeros at a rate at a half, and for the next computation, you want it to spit out ones and zeros at a rate of a quarter. Imagine you just turn the dial down, and then it just starts slowly spitting out less. So in other words, we can relax the whole idea of fixed window sizes for computation and just turn the dial gradually when the input changes. This also means that this bit stream, it's flowing in, and a bit stream is flowing out. We can turn the dial, and as we turn the dial, the input changes. The computation then produces a different bit stream, but we're also turning a dial on the output. And in principle, we could, in some cases, keep the pipe full. So we could, put in zeros and ones and keep the pipe full through sequences of the operation. Okay, I didn't explain that too well, but I'll try to later on. But the other idea is accuracy. So I'll stop with this idea. For a value of a half, how many bits do you need to decide that you have a value of a half? Well, in essence, the first bit that your circuit receives, let's say it just receives the 0, is an estimate of what the value should be. It's a very coarse estimate, but it's an estimate. The next bit that comes in gives you a slightly better estimate of what the value should be. And the value after that gives you an even better estimate. Each bit that you get gives you more precision in terms of the value. But if you look at a given circuit that computes, often the circuit has to decide to do something, like launch nuclear missiles or not. And let's say your threshold for launching the nuclear missiles is, let's say it's let's say it's a half. So, let's say your threshold is 3/4. So, if 3/4 of your stations report alert, you want to launch the nuclear missile. Well, suppose if what's coming in is all ones, then you could probably decide that with very high probability the input is greater than 3/4 after a relatively few bits come in, because each one is giving you an estimate closer and closer to 1, so you can probably decide that you're above 3/4 very early on. And you can't do this with binary radix. Binary radix will be, of course, much more compact. With a binary radix, until you've received the whole number, you, in a sense, don't know. Well, it depends. If you receive it backwards, then maybe you could know early. But anyways, the point is that with the stochastic representation, there's at least the idea that we could pipeline, not in terms of jamming the bits through, but we could pipeline in terms of accuracy, because each bit that comes in gives you a slightly more accurate representation, and then maybe you can flush to the next value of computation earlier. Okay. I'll talk about some of these ideas more, but again, as I promised, the next few lectures will be less heavy on the mathematics and the concept, and more on the concept side. Okay, we are Friday today. So the first quiz is coming, and then the first homework is coming next week.
So for this, the downside is the speed, while the upside is being that it's smaller. Can you switch from a stream to bundles? And
you can. And so that's
and does the number work out that it's fast and it's about the same size?
It does. Okay. It's not only fast, but it's potentially much faster. The reason why it's much faster is because the amount of computation that you do is you require a lot less logic. Think for a multiplier, you require a single AND gate. So in this case, you have a lot of wires, so you have a lot of computation, but you do your computation very quickly in a single step. So that's exactly right. So the trade-off is completely the reverse, where you require a lot of hardware, but you can do your computation very quickly.
Does it end up being more hardware than the binary version?
Much more.
Okay,
because
much more.
Because
and is the majority that now